discuss about thermodynamics. So basics of thermodynamics. Thermodynamics is one of the fundamental subject for every aeronautical engineer, because every aircraft depends on energy conversion to fly, whether it is a commercial airplane or a military fighter, a helicopter or a space launch vehicle. Thermodynamic principles govern how the system produce thrust and operate efficiently. In simple terms, thermodynamics is the science that studies heat, work and energy and law of governing their transformation and conservation. As aeronautical engineers, you will apply thermodynamics in many areas such as aircraft, gas turbine, jet engines, rocket propulsion system, aircraft environmental control and air conditioning system, heat exchangers used in aircraft, fuel and engine performance analysis, thermal management of aerospace vehicle. For example, when fuel burns inside a jet engine, chemical energy is converted into thermal energy. This is thermal energy increase the temperature and the pressure of the air, producing high velocity exhaust gases that generate thrust. This entire process is explained using the principle of thermodynamics. Similarly, in rocket engines, thermodynamics helps us calculate combustion temperature, nozzle performance, specific impulse and overall propulsion efficiency. Throughout this presentation, we will study the basic concept of temperature, pressure, heat, work, internal energy, enthalpy, entropy, thermodynamic system, thermodynamic process and law of thermodynamics. These concepts will later help you understand advanced subjects such as aircraft propulsion, gas turbine engine, heat transfer, CFD and aerospace thermal systems. So now let us understand what thermodynamics is actually. The thermodynamics is a branch of engineering science that studies the relationship between heat, work and energy and the laws that govern how energy is transferred and how it is transformed. In simple words, thermodynamics tells us how energy changes from one form to another. It also explains that energy cannot be created or destroyed. It can be converted from one form into another. This is the principle is known as law of conservation of energy. To understand the thermodynamics, we must first know three important terms like heat, work, energy. Heat is the energy that flows because of temperature difference. Heat always moves from high temperature body to lower temperature of the body until both reach the same temperature. For example, if you touch a hot engine after an aircraft lands, heat flows from the engine to your hand because the engine is at much higher temperature. Then work is energy transferred when a force causes displacement. Work is performed when a turbine rotates the compressor, when the compressor compresses air, or when the engine produces thrust to move an aircraft forward. Energy is the capacity to do work. Energy exists in many forms like chemical energy, mechanical energy, like etc. Thermodynamics explains how one form of energy is converted into another during aircraft operation. So next let us discuss why thermodynamics is one of the most important studies in engineering, especially in aeronautical engineering. Every engineering system either produces energy, transfers energy or uses energy efficiently. Thermodynamics provides the scientific principles needed to understand and improve this energy conversion process. Let us discuss each point one by one. First, understand energy conversion process. For example, in an aircraft engine, chemical energy in aviation fuel is converted into heat energy during combustion. Heat energy is converted into mechanical energy by the turbine. Finally, mechanical energy produces a thrust to propel the aircraft. Without thermodynamics, engineers cannot analyze this energy transformation. Second, by applying thermodynamic principles, engineers can improve engine and turbine efficiency, reduce specific fuel consumption, increase flight range, lower airline operating cost, improve overall aircraft economic. Next, thermodynamics is not limited to aircraft. It is also used in thermal power plants, nuclear power plants, combined cycle power plants. The same thermodynamic principles used in gas turbines are also applied in aircraft propulsion system. To provide a comfortable cabin environment, aircraft use environmental control system, that is ECS. Thermodynamics helps to design aircraft air conditioning system, cabin pressurization, refrigeration cycle, and it is important to design aircraft and rocket propulsion system. So this is one of the most important application for aeronautical engineers. So thermodynamics helps us to analyze the combustion chamber, design the compressor and the turbine, calculate the engine efficiency, and need to study the Brayton and Rankine cycles, etc., and to design the rocket propulsion system too. So every jet engine and rocket engine is designed using thermodynamic principles. And in modern aviation is moving towards cleaner energy sources. So thermodynamics contributes to solar thermal system, hydrogen powered aircraft, sustainable aviation fuels, fuel cell technology, like that. So next, fossil fuels or limited resources. By improving engine efficiency through thermodynamics, engineers can consume less fuel, extend the availability of natural resources, promote energy conservation. So next, as future aeronautical engineers, you will use thermodynamics to build safer, cleaner and more efficient aircraft. Now that we have understood the importance of thermodynamics, so next let us see where it is applied in real engineering systems. So thermodynamics is one of the most widely applied branches of engineering. Every system that involves heat, work, energy, conversion uses the principles of thermodynamics. Let us discuss some important application. Number one, power generation. Power generation, one of the major application of thermodynamics is in power plants. In thermal power plants, coal, natural gas or other fuels are burned. Heat is used to convert water into high pressure steam. The steam rotates the turbine, boiler efficiency, turbine efficiency, overall plant efficiency, fuel consumption. The goal is to generate maximum electricity while using minimum fuel. Next one, automobile engineering. In automobile engineering, thermodynamics plays an important role in automobile engines. In petrol and diesel engines, fuel burns inside the cylinder. Chemical energy is converted into thermal energy. Thermal energy is converted into mechanical energy. This work rotates the wheels of the vehicle. Engine performance, fuel economy and emissions are analyzed using thermodynamic principles. So next, in aeronautical and aerospace engineering, every aircraft engine operates based on a thermodynamic principle. For example, air enters a compressor and it is compressed. Fuel is burned in the combustion chamber. So high temperature gases expands through the turbine. The exhaust gases leave the nozzle at high velocity, producing thrust. Thermodynamics is also used in jet engine, turboprop, turbojet, turbofan, rocket propulsion systems, aircraft and environmental control system. So without thermodynamics, modern aircraft and spacecraft could not be designed. Next, renewable energy systems. Renewable energy system today engineers are developing cleaner and more sustainable energy sources. Already we discussed in previous slide, thermodynamics helps to improve the performance of solar thermal power plants, wind energy system, geothermal power plants, hydrogen energy systems, fuel cells. It enables efficient conservation of renewable energy into useful power. Next, thermal equipment. Many industrial devices are designed to using thermodynamics principle. Examples: boiler, heat exchangers, steam turbine, compressor, pumps, condenser. These devices are transferred to convert the energy, making thermodynamics essential for their design and operation. These are the picture for application of thermodynamics in such areas like power plant, aircraft, spacecraft, car, air conditioning system, boats, solar hot water system, refrigeration system. Now let us understand one of the most fundamental concepts in thermodynamics. What is temperature? Temperature is a physical property that indicates how hot or how cold a body is. In simple terms, it tells us the thermal condition of an object. Temperature is related to the average kinetic energy of molecules in the substance. The faster the molecules move, the higher the temperature. Conversely, slower molecular motion indicates the lower temperature. One of the most important roles temperature is that it determines the direction of heat transfer. For example, imagine placing a metal spoon in a cup of tea, hot tea. The spoon initially has a lower temperature than the tea. Heat flows from the hot tea to cooler spoon, causing the spoon's temperature to rise. After some time, both reach nearly the same temperature and the heat transfer stops. So, heat transfer stops when the thermal equilibrium is reached. In previous slide we learned about temperature. Now let's understand what is absolute temperature. In our daily life we can use Celsius. We commonly use the Celsius scales to measure the temperature. However, in engineering thermodynamics we use Kelvin scale, which is known as the absolute temperature scale. The Kelvin scale starts from absolute zero, which is the lowest possible temperature that can exist. What is absolute temperature? Absolute zero is the temperature at which the molecules of substance possesses minimum thermal energy. At this temperature, molecular motion becomes almost negligible. According to the law of thermodynamics, no temperature lower than absolute zero is theoretically possible. The value of absolute zero is 0 Kelvin, which is equal to minus 273.15 degrees Celsius. At absolute zero, molecular motion is minimum. Next, what is heat? Heat is the energy. Heat is the energy. Already we discussed in first slide. Heat is the energy transferred due to high temperature difference between the system and its surroundings. Let us understand another important property called specific heat. Specific heat. What is specific heat? Specific heat is the amount of heat required to raise the temperature of 1 kilogram of substance by 1 Kelvin. For gases, we use two types of specific heat because gases may be heated under different conditions. Number one, specific heat at constant volume. Number two, specific heat at constant pressure. So what is specific heat at constant volume? Imagine a gas enclosed in a rigid container. Since the container cannot expand, its volume remains constant. When heat is supplied, the temperature of the gas is increases, the pressure is increases, the volume remains unchanged. Since there is no movement of boundary, no boundary work is done. Therefore, all the heat supplied increases the internal energy of the gas. Heat added is given by Q equal to mCv delta T. M is mass, Cv is specific heat at constant volume, and delta T temperature difference. Next, specific heat at constant pressure. So now imagine gas inside the cylinder with movable piston. When heat is supplied, the gas expands, the piston moves upward, pressure remains constant. Here, the supplied heat has two purposes. One is increasing the internal energy, and number two is performing boundary work by moving the piston. So the heat is added is written by Q equal to mCp delta T. So m is mass, Cp represents specific heat at constant pressure. So delta T is temperature difference. Now let us understand the concept of heat transfer. What is heat transfer? Heat transfer is the process by which the thermal energy moves from one body or region at high temperature to another body or region at a lower temperature due to the temperature difference. So heat transfer is the movement of thermal energy from the region high temperature to lower temperature with the temperature difference between two bodies or regions. For example, if you place a cold metal spoon in a cup of hot tea, heat flows from the hot tea to cooler spoon. So this condition is called heat transfer. Heat transfer continues until both bodies reach the same temperature, known as thermal equilibrium. So next we discuss about the mode of heat transfer. Three modes of heat transfer is there. Number one is conduction, and two is convection. Third one is radiation. What is conduction? Conduction is the transfer of heat through a solid without the movement of material itself. Heat flows from the hotter region to the cooler region through the molecular interactions. Examples: heat passing through the wall of an aircraft engine, heat transfer through the boiler wall. And what is convection? Convection is the transfer of heat between solid surface and moving fluid such as air or water. The fluid carries heat as it moves. Example: air flowing over the aircraft wing, cooling of an engine radiator, cooling of a turbine place using airflow. Convection can be divided into two categories. One is natural convection, and one more is forced convection. What is natural convection? Just caused by density differences. Forced convection is caused by fans, pumps, or compressors. The radiation. Radiation is the transfer of heat by electromagnetic waves. Radiation does not require any material medium. For example, heat received from the sun, heat emitted by the furnace, spacecraft receiving the solar radiation. Since space is a vacuum, radiation is the only mode of heat transfer there. So this is the pictorial representation of mode of heat transfer. This is radiation, and this is what conduction. The heat is transfer this into this, and which is convection. Movement of hot fluid within the pan. So here transfer the energy between this to this. So next, what is work? So along with the heat, another important way in which energy is transferred is through work. So in thermodynamics, work is the energy transferred when a force acts through the distance, or when a system undergoes a displacement. For example, if a gas expands inside the cylinder and pushes a piston upward, that gas performs work on the piston. Similarly, when a compressor compresses the air, work is done on the air. So SI unit for work is joule. So examples of work: moving piston in an engine cylinder, rotating the shaft of a turbine, driving a compressor, operating a pump, producing thrust in a jet engine. So these are the examples of work. Next, we discuss about what is entropy. So one of the most important and sometimes challenging concept in thermodynamics. So what is thermodynamics? In engineering thermodynamics, entropy is a thermodynamic property that measures the degree of molecular disorder or randomness in a system, the quality of availability of energy to perform useful work. So the greater the randomness of molecules, the greater the entropy. Imagine two situations: ice. The water molecules are closely packed and well organized, therefore entropy is low. Next is steam. The molecules move freely in all directions and highly disordered, therefore entropy is here high. As a substance changes from solid to liquid and then to gas, its entropy increases. For reversible process, entropy equation ds equal to delta Q divided by T, where ds is change in entropy, dq is reversible heat transfer, T absolute temperature. The unit of entropy is kilojoule per Kelvin. For specific entropy, unit is kilojoule, kilogram, Kelvin. So next, what is enthalpy? Enthalpy is the total energy of the system consisting of internal energy, flow, work. It is especially useful for open system where fluids continuously enter and leave. So enthalpy is defined as H equal to U plus PV. H represents enthalpy, unit kilojoule. So U represents internal energy, P represents pressure, V volume. So now let us study the first approach used in thermodynamics called macroscopic or microscopic approach. Macroscopic approach, which is also called as classical thermodynamics, and microscopic approach, which is also called as statistical thermodynamics. So what is macroscopic approach? So the two approaches used in thermodynamics. Macroscopic approach studies the overall behavior of a system without considering the individual molecules. Instead of observing millions of molecules, we treat the substance as continuous medium and measure only the properties that we can observe directly. These measurable properties include pressure, volume, temperature, and density, like moles. For example, if we have a cylinder containing air, we do not study the motion of each air molecule. Instead, we simply measure the pressure, temperature, volume of the air. Using these properties, we can analyze the behavior of system. This approach is called classical thermodynamics because it deals with the system as a whole. The second method is to study a thermodynamic system is called microscopic approach or statistical thermodynamics. Unlike the macroscopic approach, the microscopic approach studies the behavior of individual molecules and atoms. Every gas contains billions of molecules that are constantly moving and colliding with one another. Instead of measuring only pressure and temperature, this approach analyzes the molecular motion, molecular velocity, and the molecular collisions, molecular energy distribution. Since it is impossible to track every molecule individually, statistical method and probability theory are used to predict overall behavior of system. This is why it is also called statistical thermodynamics. Now let us discuss one of the most fundamental concept in thermodynamics, the thermodynamic system. Before analyzing any engineering problem, we must first define the system we want to study, the thermodynamic system. What is thermodynamic system? It's a fixed quantity or matter or region in a space selected for analysis. In simple words, it is the part of universe that we choose to study. Everything inside the selected region is called the system, while everything outside it is called surrounding. Everything outside it is called surrounding. The surface that separates the system, the surface that separates the system, which is called the boundary. The boundary may be real or imaginary. The combination of system and surrounding is called universe. For example, gas inside the piston cylinder. Consider a cylinder filled with the gas. The gas inside the cylinder is system. The cylinder wall and the piston form the boundary. The air outside of the cylinder is surroundings. When heat is supplied, energy crosses the boundary and changes the state of gas. Now consider a jet engine. If we select the engine as our system, air enters the engine, fuel is added, high-speed exhaust gases leave the engine. The engine exchanges both mass and energy with its surroundings. This is a practical example for thermodynamic system used in aeronautical engineering. In previous slide, we learned what is thermodynamic system, and now let us classify the thermodynamic system, and based on whether mass and energy can cross the system boundary or not. There are three types of thermodynamic system. One is open system, another one is closed system, and another thing is isolated system. Let us discuss each one in detail. In open system, it's a system in which both the mass and the energy can cross the boundary. Both mass and the energy can cross the boundary. This means the matter can enter and leave the system, and the heat or work can also be transferred between system and surroundings. Example, gas turbine, jet engine, compressor, boiler, turbine. Let's consider a jet engine. Air enters the compressor, fuel enters the chamber, hot exhaust gases leaves through the nozzle since both the mass and energy cross the boundary. Jet engine is a open system. Most aerospace propulsion systems are analyzed as open system. Next, closed system. In closed system, mass cannot cross the boundary, but energy can cross in form of heat or work. The amount of matter inside the system remains constant. However, the system can gain or lose heat, and it can perform work. But no gas enters or leaves the system. Therefore, it is called closed system. The example, gas enclosed inside the piston cylinder arrangement. Then it is isolated system. An isolated system, one in which neither mass or energy can no heat transfer, no mass transfer. Mass and energy cannot cross the boundary. It is completely insulated from its surrounding. There is no heat transfer, no work transfer, no mass transfer. Example, which is this is ideal flask, thermo flask is considered an isolated system because it minimizes heat transfer with the surroundings. In reality, a perfectly isolated system does not exist, but well insulated thermos is close approximation. So this is explanation for types of thermodynamic system. In open system, mass transfer allowed, energy transfer allowed. So examples, in closed thermodynamic system, mass is no transfer, energy transfer is allowed, no mass transfer, mass is fixed. In isolated system, no mass transfer, no energy transfer. So next, this is control mass and control volume. Control mass is fixed amount of matter chosen for analysis. The amount of mass inside the system never changes. Therefore, no mass across the system boundary. However, heat work can cross the boundary. So characteristics of control mass is a fixed amount of matter. No mass enters or leaves the system. Heat and work may cross the boundary, also which is called closed system. Okay. Next, control volume. Control volume is a fixed region in space through which mass and energy can flow. Mass and energy can flow. Unlike control mass, the amount of matter inside the control volume can change because fluid continuously enters and leaves. Fluid continuously enters and leaves. So characteristics of control volume: fixed region in space, mass can enter and leave. So heat and work can also across the boundary, so which is also called open system. Example, jet engine. Next, we discuss the thermodynamic properties. Thermodynamic properties are measurable characteristics that describe the condition of state of system. By measuring these properties, we can completely understand the behavior of system. Some important thermodynamic properties are pressure, temperature, volume, density, specific volume, internal energy, enthalpy, entropy. These are things are already we discussed in previous slide. So next, the thermodynamic properties are classified into two types. One is intensive properties and another one is extensive properties. So in intensive properties, it depends on mass, but extensive properties does not In intensive properties, it is independent of mass. Extensive properties depends on mass. Example, pressure, temperature, density. Extensive properties examples are volume, mass, and internal energy. For example, consider two identical water tanks. Each tank contains 100 liters of water. If we combine them, the total volume becomes 200 liters. So the volume is increased. So which is called extensive properties. Extensive property. However, if both tanks are at 30 degrees Celsius, the combined water is still at 30 degrees Celsius. So temperature is an intensive properties. This classification is very useful when solving thermodynamic problems and selecting and correct the equations. So next let us discuss what is the concept of state and the state postulate. State means the condition of the system, which is defined by its thermodynamic property. State, it's completely described by its properties. For example, if gas has pressure 2 bar, temperature 200 degrees Celsius, then these values define the state of gas. State postulates. It states that a simple compressible system is completely specified by any two independent intensive properties. This means that if we know any two independent intensive properties such as pressure and temperature, we can determine all the remaining properties like volume, internal energy, enthalpy, entropy using thermodynamics tables or equation. So next we discuss about what is point function and path function. Point function is also called as state function. Is a property whose values depends only initial and final states of system. It does not depend on the path or process followed by reach the final state. Let us understand this using pressure and volume, like PV diagram. PV diagram shown on the slide. Here the system changes state 2 to state 1. There are three possible paths A, B, C. Although the paths are different, the initial and final states remain same. For a point function, the change is identical for all three paths because it depends only on the end states. Example for point function includes pressure, temperature, volume, density, internal energy, enthalpy, entropy. So path function is depends on how the process is carried out. It values changes according to the path followed between the initial and final states. This is the path. This is point function. 1 and 2 are the point function. The way of A, B, C are the path function. So two important path functions are heat and work. In the PV diagram, work done is equal to the area under the process curve. Since paths A, B, C have different shapes and different area, each curve is different. Therefore, work done is different for each path. Even the system states start and end of the process are same. Similarly, the amount of heat transfer also depends on the process of path. So this is a point function or a path function. Point function and a path function. Next we discuss about thermodynamic process. So thermodynamic process is a change in the state of system from one equilibrium state to another. Depending on which property remains constant, thermodynamic processes are classified into 5 main types. Number 1 is isothermal, and number 2 is isobaric, isochoric. Isothermal means constant temperature process. Isobaric means constant pressure process. Isochoric means constant volume process. Adiabatic process, this is isentropic and polytropic process. These are the main thermodynamic process we discussed in next slide. These are the PV diagram for all the process. So let begin with isobaric process. An isobaric process is a process that occurs at a constant pressure while the volume changes. In the PV diagram, the process is represented by horizontal line indicating the pressure remains constant. The pressure remains unchanged while the volume changes. Volume changes. Initial volume is Vi and the final volume is Vf. The work done during the isobaric process is given by W equal to P into Vf minus Vi. So where W is work done, P is the pressure, Vf final volume, Vi is initial volume. Since the volume changes, the gas performs boundary work. So example, heating air inside the cylinder with a freely moving piston or heating water in an open container. Next one is isochoric process. In this process, the volume remains constant. In isobaric process, the pressure remains constant. In isochoric process, the volume remains constant. So on the PV diagram, it is represented by vertical line, that is showing pressure changes while volume remains constant. Since there is no change in volume, so W equal to 0. No change in volume, W equal to 0, that is there are no boundary work is done. So according to the first law, Q equal to delta U plus W. Here W equal to 0. Then according to the first law, heat transfer equal to change in internal energy. This means heat supplied increases, the internal energy of the system increase. So next one is isothermal process. In an isothermal process, the temperature remains constant. Temperature remains constant throughout the process. For an ideal gas, PV equal to constant, since the temperature does not change, but pressure change, volume change will happen. So since the temperature does not change, so delta U, that is change in internal energy, which is equal to 0. This means internal energy remains constant. Therefore the heat supplied to the gas is completely converted into work done by the gas. So the PV curve appears as smooth downward curve called an isotherm. So example, slow expansion or compression of gas while maintaining constant temperature by heat exchange with the surroundings. In adiabatic process, Q equal to 0, that means no heat transferred between the system and its surrounding. No heat transfer between the system and its surrounding. However, work is still done because the gas expands or compresses. As a result, during the expansion, the gas temperature decreases. During compression, the gas temperature increases. So for an ideal gas, PV equal to constant, while gamma is ratio of specific heats. The adiabatic curve is steeper than isothermal curve. So next, this is the PV diagram for all the process, isothermal process, isentropic process, polytropic process. this is for isobaric, this is for isochoric. So this is a PV diagram for all the thermodynamic processes. Next we discuss about quasi-static process. The thermodynamic equilibrium is state Next we discuss about thermodynamic equilibrium. What is thermodynamic equilibrium? It states that in which a system has no tendency to change spontaneously with the time, provided it is isolated from its surroundings. In thermodynamic equilibrium, pressure is uniform and the temperature is uniform, chemical composition remains constant. So all the macroscopic properties remains constant with respect to the time. So this is the thermodynamic cycle. This is thermodynamic cycle. So a thermodynamic cycle is a series of thermodynamic process that begins and ends. So what are the thermodynamic process in the thermodynamic cycle? Number one is compression and heat addition, expansion, heat rejection. These are all the process happens in cyclic. So pressure is returns to the initial value, temperature is returns to the initial value, volume returns initial value, internal energy returns to the initial value. This means net change internal energy is 0. So for example, examples of thermodynamic cycles are Otto cycle, diesel cycle, Brayton cycle, Rankine cycle. Next slide. So next we discuss about the main things, law of thermodynamics. What are the laws in thermodynamics? First one is zeroth law of thermodynamics. So let's consider three systems A, B, C. So consider this A, B, C. If system A is thermal equilibrium with the system C, then system B is in thermal equilibrium with the system C, then the system A and B are also in thermal equilibrium. Therefore, TA equal to TB equal to TC. So this is the statement of zeroth law of thermodynamics. If two systems are each in thermal equilibrium with the third system, then they are in thermal equilibrium with each other. This is a zeroth law of thermodynamics. Next, first law of thermodynamics. So first law of thermodynamics, heat supplied to the system is converted into increase in internal energy and work done by the system. So mathematically it was expressed by Q equal to delta U plus W. Already we discussed in thermodynamic process. So Q equal to heat supplied to the system. So delta U change in internal energy and W is the work done by the system. So the statement of first law of thermodynamics is it states that energy cannot be created or destroyed. It can only change the forms or be transferred from one object to another. So heat transfer from one to another. This is the first law of thermodynamics. And the second law of thermodynamics is it have two statements. One is a Kelvin-Planck statement and another one is Clausius statement. So in Kelvin-Planck statement, it is impossible to construct a heat engine which produces no effect other than the extraction of heat from a single source and the production of an equivalent amount of work. So in Clausius statement, it is impossible to construct a device which is operating in a cycle to transfer heat from cold body to hot body without any work input. These are the statements of, for second law of thermodynamics. So in third law of thermodynamics, it states that the entropy of perfect crystalline substance is 0 at the absolute 0 of temperature. So just third law of thermodynamics.